great. Very good. Okay, so welcome everybody to the first Shocklab talk for, I guess, a couple of weeks. We are extremely happy to have Gokul Swamy here, who is a PhD student at the moment at Carnegie Mellon, despite currently being in Seattle. But yeah, he's been doing some extremely interesting work in reinforcement learning, particularly in terms of offline reinforcement learning. And he's going to be talking about some super interesting work today about interactive imitation learning. So over to you. Thank you.
Yeah, thank you for the kind introduction. So I guess one thing I should mention is I can't actually see the Zoom chat during this whole thing. So if you have a question, feel free to just speak up, or I can kind of look at messages at the end. The other thing I should mention here is normally when I give this sort of presentation, I normally have two monitors. I have one monitor on which I can actually see my slide notes. So I'm doing this one because I only have my laptop with me entirely off the cuff. So apologies in advance if I seem to say something that doesn't make sense. It's probably on my end, and please ask me to clarify. Okay, so let's go ahead and get started then. So broadly speaking, the work I'm going to be talking about today is about how we can learn to make sequence of decisions from data. So I think there's, relatively obvious applications of these sorts of things, like things for like self-driving cars and the like, but I think the same kind of underlying algorithmic principles apply much more broadly to things like recommender systems and sort of the growing set of large language model chatbots because of repeated interaction with the same user. So today I'm mostly going to be talking about a paradigm for learning to make sequential decisions from data called imitation learning. So with apologies for using the word crash here, I'm going to talk a little bit about how we could try and get a self-driving car to be able to drive around. So kind of very broadly, right, we are going to strap some, drivers in cars, and we're going to, instrument those cars with different sensors like lidars and cameras. And then we want to have some sort of algorithm that can take all that data and learn a policy that allows the car to drive itself. So let's think about this sort of a more toy version of that problem. So let's say we just want to get this car to drive laps around this track. So the simplest possible way we could try thinking of doing this is effectively by treating this problem as a supervised learning problem. So let's say we think of our cars being featurized, or let's say we get our expert to drive laps around this track. And let's say our car has some state, it's XY position, something like that. And the actions we record are something like, how much the expert, turned the steering wheel, how much they press the gas and brake pedals. And then what we do is we just regress from collected states to collected actions. So this is just a pure supervised learning problem. And to make it more concrete, let's say we did something simple, like we just picked a mean squared error criterion, something like this. So this sort of approach in the literature is usually called behavior cloning. So this seems like a fine and dandy approach, but when you actually try it in practice, you'll often observe something kind of odd. So what you'll see is that the car, will probably not make every decision perfectly. It'll make some small mistake early on, and then it'll end up in a state in which it hasn't seen any data before. It doesn't have any idea what to do, and it'll make another mistake, and it'll keep seeing mistakes happen over and over again. So you'll kind of end up going off the rails over time. So this is the phenomenon known as compounding errors. And intuitively, I think the way to think about this is that during training time, you only saw data from the expert state distribution, the sort of green track here. But then at test time, when you're rolling out your policy, if you end up in a state the expert didn't visit, then you might have no idea what to do, and you don't know how to recover your own mistakes. So this is really a sort of a distribution shift. If you have a bit of a machine learning background, more specifically, it's a form of covariate shift, where the sort of state distribution, the input distribution here is changing, while the conditional label distribution, action condition on state, is constant. So the question is, okay, how do we fix this problem, right? And I think, basically just one trick I'm going to be talking about today. I'm going to maybe get into a couple of details of it, but really I think the core insight is just that if we're able to actually roll out the learner's policy into the environment and actually see where we end up, we can effectively generate samples from the test distribution. We can actually see what states we induce via our own policy. And I think this is really the sort of the kind of key insight here. And I think the reason this is a really interesting insight is that, in in full generality, the problem distribution shift is really hard to solve, right? Like if I test you on an input you've never seen before, how are you supposed to know what the correct label is? So the question, I think, is really, given we can actually generate samples in the test distribution here, given we had that ability, the interaction with the environment, how do we then use that data and information to make sure we learn policies that generalize well? And I'm going to talk about a couple of approaches for doing that now. So perhaps the simplest approach you could think of is something like, I get my set of, learner states and actions, I get my set of expert states and actions, and I try to minimize some notion of divergence between these two. So the way I like to think about this is effectively it's like you're doing a GAN, but in the space of trajectories. So our generator here is like a policy coupled with the world model to actually give us trajectories. And our discriminator here tries to differentiate between learner and expert trajectories. And then so our policy update here is basically doing reinforcement learning with the discriminator as a learn reward function. And our discriminator update is basically looking at the new batch of learner data, comparing it to the expert data and training a classifier. So these sorts of approaches are known as inverse reinforcement learning. And I'll make this a bit more formal in a bit, but intuitively, you should expect these approaches to be more robust to compounding errors because you're actually seeing samples from the test distribution because you're doing rollouts in the environment here. So this is sort of one family of approaches. And then the sort of kind of other perhaps natural thing to do here is well, let's say we roll out our policy and we're able to further query the expert. So we could ask them at this state, how much would you have turned the steering wheel? How much would you have like pressed the gas pedal? And then sort of iteratively train on this data. So we get our learner states and we get expert action labels, and then we just regress between these. And we do this iteratively over time. And then we sort of aggregate our data. And this is usually called, these are called like Dagger or data set aggregation. I think there's maybe two things to think about here. One thing is that effectively we're solving the covariate shift problem here by getting labels on the test distribution, right? Because we're just asking the expert, what should I have done in this state? The other thing that I sort of important here is you also want the policy you're like rolling out to stabilize over time, or else you might need to keep getting new labels. So that's what this sort of data aggregation here is doing. If you have a bit of an online learning background, what we're doing is we're running a bit of a no regret algorithm, like either like follow the leader, or I guess really follow the regularized leader to sort of stabilize the iterates over time. So sort of bringing it all together, we kind of have a taxonomy of algorithms for imitation. We have offline algorithms like behavior cloning. If you access the environment, you can instead run online algorithms like inverse reinforcement learning that are comparing full trajectories. And then if you have access to a queryable expert, you can run algorithms like Dagger that are, trying to minimize the difference between learner and expert actions on states and learner rollouts. So I'm going to now be talking a little bit about some details here about compounding errors and how we do this sort of stuff efficiently. Before I do, does anybody have any questions?
Yes, maybe I can ask a quick question.
Of course.
So for sequence modeling, there used to be this, well, I think it's often the standard thing called teacher forcing. I wonder if is that roughly the same idea as behavioral cloning?
So I think if I remember correctly, I think teacher forcing is a little bit closer to Dagger, but I don't remember off the top of my head. I need to double check, but I would say that I think I think the one that's really close in the NLP field is it's called like scheduled sampling or something. I think that is effectively Dagger. And I think just a sort of like standard, next token prediction style thing. You have some prefix and you just want to predict the next token. I think that's much closer to behavior cloning, if that makes sense.
Thanks.
Yeah.
Maybe I can ask
any other questions?
Yeah, maybe I can ask a quick question here. So here, with the ability to query the experts, I can imagine that there are sort of multiple policies of ways to explore the potential test sort of test set state of the environment? Are there aspects by which one might use curiosity type algorithms to look at particular parts of the state space that the agent isn't particularly aware of in order to learn as much information as possible from the expert?
Yeah, I mean, it's a good question. So I would say sort of in the sort of classical imitation learning kind of setting, right? Your goal is to avoid exploration as much as possible because it's often, costly and expensive. But if you actually are interested in, basically getting data kind of all over the space and you're able to actually query the expert, yeah, I think a very natural idea is, something like training an ensemble of learners and looking at their disagreement, and if it's above some threshold, querying the expert, something like that makes sense. I think it also depends, I guess, a bit on what information you have. Like I could imagine if you have access to some sort of reward signal, you might be able to say that, okay, I only want to query the expert in states where I know the learner is being somewhat suboptimal. But if you're just doing a general exploration problem, then off top of my head, I don't know of something more reasonable than effectively a kind of curiosity or reward-free exploration kind of technique.
Thank you.
Yeah, of course. Any other questions? Cool. So now I'm going to talk about I guess, and each of these kind of fit into a family of algorithms. There's offline algorithms, online algorithms, and interactive algorithms. So now I'm going to maybe try and talk about what I think sort of is the kind of meat of the sort of work I've been doing over the last few years, specifically on kind of on the efficient algorithm side of things. So I'm going to first talk a little bit about sort of kind of, I think, the sort of complete story with respect to compounding errors. Next, I'm going to talk a little bit about sort of computational efficiency. Computational efficiency here meaning I want to learn policies that are robust to compounding errors without having to spend a lot of time interacting with the environment. And then I'll talk a little bit about statistical efficiency. So if I have a kind of small set of expert demonstrations, how do I still learn well? So let's kind of start off by talking about compounding errors. So I think that when we sort of like try to think about kind of fundamentally what we're doing here in imitation learning, what we want to do is basically we want to learn a policy that matches the expert's performance of policy phi, that matches the performance of the experts, i.e. The challenge though is that we don't actually know the objective function, right? We're trying to match expert performance purely on the basis of demonstrated behavior based on the rollouts we saw. So this is a really hard question, I think, in general, but I think what makes it easier often in practice is that we often know something about this function, right? Like for self-driving, we know it might depend on things like avoiding other cars, respecting speed limits, rather than something like the phase of the moon. This means that we can often, roughly specify the class this function lies in, and then we can attempt to do well under all functions in this class, given we don't know which one is the one we actually care about, or equivalently, we can attempt to do well under the worst case function in this class. Sort of leads to the form of a two-player zero-sum game. And basically, you can sort of recover each of the family of imitation learning approaches I talked about earlier by basically doing a different sort of way of writing this sort of particular game payoff. I am, in the interest of time, going to skip the slides where I do the derivation of this point. But if we have time at the end, if anybody's really curious, I'm more than happy to talk about it. It's just the sort of thing where I think if you see it for the first time, it's like kind of confusing, and it's something that's best kind of you kind of sit down and think about it on your own. So I'm not going to go through a couple slides of math extremely quickly. But basically, you've got this sort of kind of two-player zero-sum game things, which correspond to the online problem, the offline problem, and the interactive problem. So I think the kind of there's maybe two kind of, I think, really interesting takeaways from this sort of kind of game solving perspective on imitation learning. The first is that because I can write like basically every algorithm that is offline, online, or interactive as solving this game, I can do analysis that applies to all algorithms in each of these families. So I can sort of say that, okay, all offline algorithms must suffer from compounding errors. Just really nice, because I think a lot of the work that had been prior to this was really kind of doing a case-by-case analysis. So maybe the sort of takeaway here, right, is that for offline algorithms, you have this sort of epsilon t squared compounding error thing that in the worst case is not avoidable, purely based on offline data. For online algorithms, sort of the inverse reinforcement learning style of things, you were able to be robust to compounding errors. For the interactive algorithms like Dagger, you see the epsilon t, that makes sense. T is the horizon of the problem here. H is this this thing called the recoverability constant of the problem. I'm not going to talk about the details now. I'm happy to clarify it later if someone's curious, but basically it sort of captures how well the expert is able to recover from an arbitrary learner mistake. So you can expect that if you're getting guidance from the expert, but like the learner can just fall off a cliff, like it's not going to be very helpful guidance. There's some sort of notion of the actual structure of the MDP that matters there. So this is sort of maybe the kind of high level sort of compounding error takeaway here. And I think maybe the thing I'd like to point out is, at least looking at compounding errors, it seems like the sort of online algorithms here are sort of the best. The sort of other interesting thing we were able to do was we were able to actually, design algorithms that worked quite well, that were basically very directly trying to solve one of those three games. So we have three different algorithms here, all named after some kind of medicine. I was very proud of this at the time. Advil here is an offline algorithm. It basically looks like training a Wasserstein GAN between data from the learner and data from the expert. Adril here is basically doing inverse reinforcement learning, but not actually learning a reward function. You can actually just effectively look at data in your replay buffer and just set the rewards in a very particular way. This has a really nice interpretation as basically being a functional gradient. It also works like very well in practice. I actually haven't seen someone do better than this yet. So we're really happy about that. It's a nice trick. I hope people use it more. And then Gokul here is effectively sort of an adversarial version of Dagger. So instead of doing regression, you basically train a discriminator and use that as your loss function. And that for certain problems can work better. So I guess sort of in short, really the kind of contribution to this part of my work was really the sort of first sort of complete characterization of compounding errors for imitation learning, and also designing kind of provably efficient algorithms for actually achieving those error bounds. That was sort of a lot. Does anybody have any questions before I move on? Cool. I should also note I haven't actually timed this talk, so it's possible I go way under or way over. And if I go way under, I have a backup talk I could talk about more stuff about. And if I go way over, I apologize in advance. So now let's talk a little bit about computational efficiency. So, the sort of benefit of the sort of inverse reinforcement learning kind of family of approaches, right, is that they are, robust to compounding errors. That's sort of what the derivations we did on the last slide were saying. The sort of issue with them, right, is that they require repeatedly solving a reinforcement learning problem. So every iteration of that algorithm is basically picking a new reward function in an outer loop, and in an inner loop, optimizing that reward function via reinforcement learning. And if you think about this, this is really weird, right? Like we've reduced the easier problem of imitation learning to repeatedly solving the harder problem of reinforcement learning. So that doesn't feel right. And our question in this work was, well, how do we do this in a way that is more computationally efficient? So computationally meaning here, we want to minimize the amount of learner environment interactions. So just to sort of refresh everyone's memory, right, inverse reinforcement learning for imitation learning is a sort of GAN-like thing where you basically have, your policy being a generator, a couple of the world models actually give you trajectories, and your discriminator being between learner and expert trajectories. Cool. I think there's another question in the chat. I might be just seeing things though.
That was just if there's time to go back to talk about the Adril algorithm. You said you hoped people would use more. I'd be interested to know a bit more about that, but just if there's time later.
Yeah, of course. First, please remind me at the end. I'm more than happy to talk about it. So right, so we have this sort of the setup, right? And just remember here, our discriminator update here, which is sort of an outer loop, is trying to pick a reward function, basically maximally distinguishes expert and learner trajectories. And our policy update here is basically doing reinforcement learning with that learned adversarially chosen reward function. So let's go through an example, or maybe let me sort of once again sort of say this one more time, right? It's the benefit is robust to compounding errors. The downside is we have to repeatedly solve an RL problem. So the question you're trying to solve now is basically how do we stay pretty robust to compounding errors without having this sort of heavy computational burden? And I think, right, the sort of point I've been saying repeatedly over the last few slides, and so I want to say one more time, is it's the reinforcement learning part that makes inverse reinforcement learning inefficient, because you have this inner loop that requires a lot of optimization. So let me try and give you a concrete example of this. So let's say the learner is operating the sort of binary tree MDP. So they start at the top, and at each time step, they can either go left or right, and until they get to the bottom of the tree, which let's say is of some depth h. And let's say we constrain the adversary here, the discriminator, to basically pick reward functions that are 0 everywhere, except for one of the leaf nodes. And let's say on the first iteration, the adversary picks this reward function. Then to get any reward on this problem whatsoever, the learner needs to visit every single leaf node in this tree, of which there are 2 to the h. So already on the first iteration of this procedure, we already have an interaction complexity that is exponential in the task horizon. Then, at every future iteration of this procedure, you would again need to solve a problem from scratch, where we need to basically explore this entire tree to find the reward in one of the leaf nodes. So we'd have a kind of crazy amount of sort of interaction we actually need to do.
Sorry, can I just ask that?
Of course.
In one of the previous slides was the horizon length actually t? Was it the other way around?
Yeah. Yes. You're totally right. Yes, I should have fixed that. Thank you for mentioning that. Yep.
Good.
So h previously was a recoverability constant. Here it's the horizon. Yes. Thank you for asking that. Right. So here we have this sort of thing, and over we need to solve this whole reinforcement learning problem. So I think the sort of kind of key insight here is that, when we're sort of exploring this entire tree, trying to find any sort of reward, right, we're going to try a bunch of different policies that are very different from the expert's policy, right? And if our goal is to actually imitate the expert, we only need to compete against policies with similar state visitation distributions to that of the expert. And the question becomes, okay, how do I basically kind of focus my policy search on, just on states that are, close to where the expert visited? And a very simple idea as well, what if I just reset the learner the states from the expert demonstration? So instead of sort of having this sort of unnecessary exploration over the entire tree, maybe if I tell you the expert always goes left, that, okay, I only really need to look at what decision I'm making on the leftmost path rather than for the entire rest of the tree. I'm going to talk about how we actually do this more formally in a second, but just the sort of high-level idea here makes sense. Cool. I'm going to give you a particular algorithm for doing this. So let's say the expert here does what I said and always takes the sort of left path here. So we're going to do a sort of algorithm that is effectively a form of dynamic programming. But rather than doing this sort of standard Bellman style dynamic programming in terms of Q values, here we're going to do it in terms of policies. So to make it a little more clear what I mean, at the sort of first step of this algorithm, what we do is we sort of pick a state on the second to last time step of the expert visitation distribution, and we try to learn a policy that makes a single decision going left or right. And the way we do this is where we solve a game where we have an adversary that discriminates over trajectory suffixes of length 1. And if we were to solve this game, right, we'd learn that, okay, if I ever pick to go right, the adversary can penalize me. So I'm going to pick to go left. Then what we do is we, lock in this policy. Then what we do is we back up a time step and we try to learn a policy here that makes a single left to right decision and then calls pi 3 that's already been fixed. And we try to learn, and we do this by picking a discriminator that differentiates over trajectory suffixes of length 2. So we're still learning a single policy here, but our discriminator here now gets to see the entire suffix. So we get to see both the effect of pi2 and pi3. Then we lock this policy in, back up another time step, lock that policy in. And if you think about it, right, at each time step, we're basically not having to sort of explore this entire tree, right? We're only making a single left-right decision. And there's t time steps because each time step is, has interaction that's linear in the task horizon, and there's t iterations overall. Our overall interaction complexity is just 8 squared, so the task horizon squared. So instead of having this sort of exponential complexity, we have a polynomial complexity instead. Before I kind of talk about why this is interesting and important, does what I'm suggesting here make sense? Cool. So I think the sort of the reason this is, I think, particularly interesting for this approach, right, is that like the reason reinforcement learning has such a kind of awful sample complexity at time is because you need to actually explore quite a bit, right? That's really what sort of makes you pay in terms of interaction. But here, I roughly know where I want my policy to be, right? I have these sort of expert demonstrations that are given to me. So I don't actually need to do exploration. I can just kind of focus my policy search here. So the sort of kind of real takeaway here is that by basically taking out the RL inner loop, and basically by using this algorithm instead, we're able to basically kind of give the first sort of general polynomial time algorithms for this problem. General here meaning that like if you like the problem's like fully linear, you can like just do an LQR style thing, but for general MDPs, it's a bit more complex. So the algorithm I just described, we called MMDP, or moment matching by dynamic programming. Perhaps the issue with that algorithm is you need to learn a sequence of policies, which can be kind of annoying if your task is one with a really long horizon. So we also give an algorithm that requires learning a single stationary policy we call NRMM, or no regret moment matching. I didn't go through it because I think the intuition is much less clear, but effectively what it says is basically do something that looks like inverse RL, but change the reset distribution of the RL inner loop to be states from the expert's visitation distribution. So instead of just trying to start from the top of this, snake-like thing, we would start from somewhere in the middle. And we learned that, okay, I really need to focus on doing policy improvement on states from the expert's state distribution. That's sort of the kind of the insight here. Well, I think the sort of, yeah, I guess one of the things I should mention here, which I think is sort of interesting from an algorithmic perspective, is that so kind of if you put on your game solving hat, right? One way you can try and compute an Nash equilibria is you basically have one player follow a sort of no regret strategy, and the other player either follow no regret strategy or do best responses. What's really interesting here is the policy player is doing neither of those, right? Because the algorithm I just described, when you're doing this sort of dynamic programming search, it could be really suboptimal for the particular word function that was chosen. So it's not actually a best response. But because I know that the expert's policy is actually like a kind of an equilibrium solution for the game, I can actually just use this more efficient optimization procedure. So it's really interesting. It's like from a sort of game solving perspective that we're actually, computing an equilibrium without actually doing a full best response, which I think is really cool. Sort of on a more practical level, I think this algorithm like works very well in practice, which we were really happy about. So this is kind of one of the sort of offline RL things. I am, I'm actually interacting with the environment here. So we picked one of the sort of Ant maze tasks. And so our algorithms here are in, teal and orange. What you'll see is that compared to a standard inverse RL baseline, which is here in gray, we're like far more sample efficient. And I might be wrong about this, but to my knowledge, I think this is the best performance someone has ever gotten on this task without using any award information whatsoever. So we're really happy about that. I'll also note that if you're familiar with sort of this particular offline RL benchmark, you might think the behavior cloning performance here is unusually high. I'm happy to talk about why that's true. I think I think a lot of people have just implemented their baselines quite poorly for this problem, actually. But yeah, I think really the sort of insight here is that for these problems that are hard exploration, like solving a maze, we don't actually have to solve the whole maze. When I give you basically a path through the maze, you can do policy search much more efficiently. So you see a much kind of lower level of sample complexity here. And then if I pick problems where, exploration is less of a challenge, like the sort of locomotion style things, you still see a benefit. It's not as drastic of a benefit, you still see a benefit. So I think really the sort of takeaway for me at least is that if you're actually doing learning in simulation, where you can actually reset the learner to a state, this is probably the right thing to do. And it also stacks nicely with any sort of like online imitation learning algorithm. So I think what I'm really hoping is it just becomes like a standard like ingredient that people use moving forward. Because I think it just makes everything better, and you actually keep pretty strong guarantees while doing it. So I think maybe to summarize that up, it's really sort of the contribution to this is the first polynomial-time algorithms for the general inverse reinforcement learning problem. So before I move on to the last part of my talk, does anybody have any questions?
Yes, I had a question. I've just posted it in the chat, but I don't know if this is quite the right way of thinking about it. But certainly with sort of traditional offline RL, often the agent can end up with a policy which is actually better than the data generating policy, which has created the data set that the agent is learning from. It feels like in this case there's a sort of limit on a limit of the expert's ability. Is there any way to combine this with something that allows an agent to potentially get sort of better, even more optimal behavior than the expert? I guess the fact that there isn't sort of the reward function defined ab initio means that that's kind of difficult because there is no optimal if there is no defined reward function for the agent. But is there any sense in which you can do better than the expert?
Yeah, good question. So one thing I'll say first is that I think that in offline reinforcement learning, I think on like a problem that's not a very sort of toy benchmark problem, I think it's really hard to truly do much better than the expert. I think that you have like a pretty ridiculous level of covariate shift whenever you're solving an offline problem. So I don't know if I really believe if a lot of the trajectory stitching style arguments really would hold for more realistic problems. I think that it's almost like I give you a dictionary and ask you to spit out Shakespeare, right? Like it's a very challenging thing to do in some sense. That being said, I think the question is still interesting of whether we can actually do better than the expert. So I think you're totally right that without any extra information, it's like, well, how would you even figure out that you're doing better, right? So if you have access to rewards, I think there are really interesting things you can do. So the algorithm we're actually like running here in the inner loop is an algorithm called policy search by dynamic programming, or for the stationary policy version, it's one called no regret policy iteration. And both of those algorithms actually assume access to reward function. So I think those are actually sort of the right algorithms for kind of combining data from an expert to reduce exploration, but also combining reward signals. I think though that if you want to really be better than the expert though, I feel like the right approach would be effectively to fit something like a Q function based on their words, both on data from the experts rollouts and both on data from like learner rollouts. And basically, if you see yourself doing better than the expert, then you shouldn't be taking guidance from the expert anymore on that particular state or that particular part of the problem. So I guess what I'm trying to say here is that I think that there are algorithms where you can combine the RL signal with the data from an imitation learning agent. And I think that's sort of the kind of baseline algorithms we're sort of calling in the inner loop here. But I think for both of those algorithms, because they ultimately end up trusting the expert, it's very hard to do like much better than the expert. So I think what you would need to do is basically have the learner effectively have a way to figure out, are they doing better than the expert or not, and then use that to figure out if they want to actually do policy improvement, or if they can just basically kind of try to mimic what the expert was doing. Does that sort of make sense?
Yeah, absolutely. Yeah, thank you.
Great. Yeah. Any other questions?
I guess on that, I think on the previous slide, the ant maze game, if you can go to that.
Mm-hmm. Oh yeah, of course.
Yeah, so
yep.
on the right-hand side, is that green line the policy of the expert? Am I correct in seeing that?
Yes. Yeah, for the play data, I don't actually know if there's a well-defined expert policy. So yeah, that's why I didn't add the line in. Yeah.
Okay. Yeah, I was just wondering what the spikes above that mean in terms of the gameplay, if it's sort of like average reward or not.
I think the spikes above that line, above the green line, I think those are just like finite sample things.
Okay.
Like
cool.
I'd be very surprised if you were actually reliably doing better than the expert. That'd be weird. I should note that, like, for example, for the Hopper problem here, the expert policy is just a policy trained via reinforcement learning for a while. So it would be, I don't know if it's like literally the optimal policy, but it's a very high reward policy. So it's pretty hard to actually do better than it on this problem.
Right. So it's sort of baseline. Yeah. Good to know.
Yeah. Cool. Thanks. Any other questions? Cool. So last I'm going to talk about statistical efficiency. So this is really how we can try to make the most out of a sort of finite set of expert demonstrations. So one of the things that kind of swept under the rug in both of the previous papers is I actually assumed I had an infinite number of expert demonstrations, which of course you don't actually have in practice. And the question is, how do you actually handle the finite sample issues here in an interesting way? So I'm going to give you guys, I think, a very sort of high-level picture of this algorithm. The proofs for this particular paper are rather painful, so I don't really want to go through them. But I'm going to try and give you guys maybe a flavor, because I think the eventual algorithm we derived, I think, is actually a very reasonable algorithm. So let's say we're trying to estimate expert moments with limited demos. So let's say we think about, just for a single trajectory, what the sort of generative process is, right? So, the learner takes some action, the expert takes some action, the MDP transitions to the next state, the expert takes another action, so on and so forth, right? And if you sort of think about this sort of generative process for a second, right? If we're in the interactive setting, we can actually, interact with the environment, try out action, see where we end up. We actually can sample from the transition distribution here, right? Like, the only uncertainty we actually have is in the expert actions at particular states, when we think of the uncertainty over the whole sort of trajectory distribution. Like, if you think about it a bit further, you might be able to localize the expert's action uncertainty to certain states, right? You might say that maybe on the first state, because you always start at the same state, for example, you know very well what the expert's action is. But maybe further on, because there's more variance in where the expert ends up, you're less sure of what to do. And if you're thinking of maybe like a concrete example of this, the one I like to think of is, think of something like, you're doing self-driving, and when you're on the highway, right, it's usually very clear what you're going to do, which is drive forward at a constant speed. But when you're doing merges in and off the highway, right, there's much more variability in what you actually want to do. So there's sort of a notion of, okay, we probably are very confident of what the expert action is at these kind of states on the highway, but for the sort of on-ramp and off-ramp, it's a little bit less clear. So the question then becomes, okay, how do we actually localize this expert action uncertainty? So let's think about the simplest possible problem here, which is a problem with fully deterministic expert. So the expert always plays the same action in the same state. And let's also say we're in a tabular problem, right? Then here, right, it's very clear where we have kind of expert action uncertainty, right? Like in the states where we've seen the expert play an action, we know perfectly with full confidence what their action was. And as soon as we get out of that set of states, we have no idea what it is. It's very clear, right? And the question becomes, well, of course, when we want to solve more interesting, challenging, continuous problems, how do we kind of have something similar to this. And our insight was basically that we can look at the disagreement of a set of BC policies. So if you think about it, on this tabular problem, if I was to run behavior cloning, just supervised learning, regressing from states to actions, I would be able to figure out that in all of these states, there's only one like label. So I'm going to fully regress and just match, right? But if there was any sort of stochasticity and I wasn't sure about what the actually was going to do, if I train an ensemble of policies, they'd be more likely to disagree. The sort of generalization of this to the continuous setting is really trying to figure out this kind of set of places where we are confident of the expert actions, which is where basically our BC policies seem to really agree with each other. And then kind of outside of that is where our ensemble BC policies kind of don't agree with each other, or they don't necessarily therefore agree with the expert. So I'm gonna now give you a practical algorithm that kind of tries to utilize this insight. So we call this algorithm replay estimation, and it looks like this. You train a behavior cloning learner. You do rollouts in the environment with this learner. And you add these rollouts to your expert data set, and you associate a weight here that confident you are of behavior cloning's actions. So the theory is a bit agnostic to this, but you can use whatever uncertainty measure you want. In our practical experiments, what we did was we basically trained an ensemble of policies and basically looked at the disagreement between these BC policies. And then you basically perform sort of a weighted mode matching procedure on this sort of aggregate data set. So this algorithm might seem kind of like one I kind of pulled out of nowhere, but it actually does have kind of surprisingly strong theoretical properties. I'm going to skip this slide just because I think it's a little bit less necessary. It's actually sort of the minimax-optimal algorithm for this problem. So like on the worst case MDP, it is the best algorithm to run. The proof of this, as you can guess, was very annoying. And if you're sort of looking at it from the settings where we can actually do analysis, like linear and tabular problems, you can basically see plots like this where replay estimation here has a curve in orange, where the maximum difference between learner and expert performance, lower bounds, that where you would get either from behavior cloning, which is here in gray, or from mode matching here, which is inverse reinforcement learning, online imitation learning, here in teal. And the algorithm in practice works okay. I mean, we picked problems where behavior cloning was doing better than a standard mode matching algorithm. So I don't think it's terribly surprising that if you put data from like that policy into your data set, you end up doing better. I haven't actually tried this algorithm on a more challenging problem, but I think one of the reasons I like it, at least in theory, is that like usually when someone describes the minimax-optimal algorithm for a problem, it's an algorithm that you'd never actually want to run because it's like something that is just dealing with this really weird edge case that can happen. But I think basically using behavior cloning combined with a simulator to do data augmentation to basically kind of marginalize out the uncertainty at states where you're confident of the expert actions is a very intuitive and reasonable idea, and one that I would actually kind of think that in practice could be a thing that would work. Yeah, so I think that is sort of all the slides I had provided. I mean, really, the summary here is that of the work I've been trying to talk about for the last 45 minutes or so has been that really we kind of now have computationally and statistically efficient algorithms for imitation learning that are robust to confounding errors. So with that, I'm more than happy to take any questions. I'm more than happy to talk about other stuff. But yeah, thank you again.
Wonderful. Thank you so much. That was wonderful. Great. Yeah. Are there any questions at the moment?
Yeah, I think I was just and it's funny, it's just before you went into the last part about sort of the assumptions that you have about the experts, I was going to ask, I mean, I think there are just about this is a new area of reinforcement learning for me in particular, but I was going to ask, I mean, there are sort of obviously lots of assumptions that you make about experts and what sort of what experience they have and where they diverge, and are there I mean, I suppose I was thinking about so the first question is, I mean, in the real world and real world problems, like how is the process of gathering expert data must be very difficult, and how can you be sure that that there aren't gaps almost in like the expert's experience at like critical sort of points in the environment, like falling off a cliff, you know, in the very simple examples. And then like, do you think that are there examples of using sort of like a in fact, I don't know if it's got to do with the same thing, but I read something about mixture of experts, but I'm not sure if that's like, I mean, if you've got several experts and sort of got to learn, you know, some kind of like weighted policy between them, does that solve some of those issues?
Yeah, so I think you asked two really good questions there. So the first is sort of like, well, you know, if my expert data isn't great, you know, how do I deal with that, right? And I would say I think this is sort of not a problem that's unique to imitation learning. I think it's a problem that affects kind of all of machine learning, right? Like, you know, if you have bad data, I don't know how you're actually going to learn well. I will say that like in practice for like, you know, let's say something like self-driving, what you do is you just pay people who are very good drivers, and you also pay people to kind of clean the data and make sure it's good. So I think that you know, it's a thing that it's not a thing that's trivial, but it's a thing that I think really can be solved with sort of a good amount of effort. I think for sort of like more smaller scale academic things, where you know you sort of just want to show that the method works rather than, you know, actually as a real world deployable system. I don't think it's really that difficult to collect data well. I think really when it comes to actually getting robots to do things in academia, I think the vast majority of successes have come from some kind of imitation learning.
Okay, interesting.
Then your second question was about sort of, so I think a mixture of experts is a little bit different, but I think the question that was underlying it is very interesting, which is, let's say I have data from multiple expert policies. What do I do? So I think that if you know, you don't have any sort of way to do tie breaking, it's very unclear of what the right thing to do is. But if I give you access to a reward signal or some sort of thing that, you know, ranks these things, what I could do is basically, you know, do something that is almost like fitting a queue function at a state for each of these expert policies, and then just picking the follow the one with the highest Q value. Like that's a very natural algorithm to run. There is a paper by some very smart folks from, I guess now they split between Microsoft and Google Research called Mamba that does this. And I think that is essentially what I think the right approach is for that sort of you have multiple experts problem. I think it also, I think you brought up a really good point, which is that, you know, maybe you have experts that are good at different parts of the problem, different parts of the state space. And then I think it's very reasonable to be like, okay, what I want to do is basically figure out which of the experts is the best for me to sort of try to imitate or take guidance from. And I think, yeah, the sort of techniques they use in that paper, I think are effectively correct.
That's really interesting. Thanks.
Yeah, of course.
So as a follow up on that, I guess you could have different experts. Let's say an expert is someone who has full knowledge of the environment and then can follow a greedy policy or some other policy. I guess the question is, you could have two experts where one is being conservative, maybe it's trying to avoid certain situations, whereas the other one might be trying to maximize reward throughout the environment. So if you, let's say you're just trying to maximize Q value, that might not work out so well. I wonder if you have any thoughts there, like how you would weight that or consider that in terms of trying to learn a reward signal.
Okay, let me think. So I think you're saying that there are two experts here. One that is sort of the actual optimal policy for the problem, and one that is, you know, so trying to maximize the expected reward, maybe is, you know, trying to solve a more constrained problem or trying to minimize, you know, variance or, you know, some sort of other risk measure. Well, I think if you have, those seem like at some level, I think of, they seem very different problems to me, like what the actual policy might want to do. So I think you would have to basically make a choice, you know, which of these two behaviors is the one I actually care about, you know? Like if I actually care about maximizing a word, then I should do that. And I think that, you know, right, the sort of thing you can do here is that this also can be done for whatever task it is that you want, right? Like you can, if you just have expert data from these two different policies, you can just relabel them with different rewards based on whatever it is the function you actually care about is. So I think that that's really a question of, you picking a tie-breaking mechanism based on what the actual behavior you eventually want is.
Yeah, that makes sense. Thank you.
Of course, yeah.
So I have a question, which is whether this has been looked at in the multi-agent setting at all, and how it extends to that setting.
Yeah, that's a great question. So one of my advisors wrote a really fantastic paper on multi-agent imitation learning back in the day. I think it's called the inverse equilibrium problem. It's a beautiful paper. I think it won best paper at ICML. I think that paper, at least in my mind, is sort of the high point in the field. I think that of multi-agent imitation learning. I think they really nailed the problem. I think since then there's been a lot of folks who have basically tried to do the same thing with deep networks instead, and I think that's fine. But I don't know if I've actually seen someone make a conceptual breakthrough since then.
Mm-hmm.
I would say that I also think it's a problem. It's a problem that's really interesting to me and it's worth thinking about, because actually it was the problem I first started doing research in. But well, what I'll say is that a thing that works pretty reliably in practice for real self-driving cars is basically you learn a predictor of what all other agents in the scene are going to do, conditioned on the sort of ego policy's actions. So imagine something like basically like a conditional transformer VAE, whatever you want, but that basically learns that sort of predictor thing. The important thing here, right, is that you are learning to predict others' actions based on your own action. Because if you just predict just sort of a joint distribution over all actions, right, then if you change your policy slightly, right, then you might kind of throw everything out of equilibrium. So I do think you want to sort of have an action conditional model. So I think that's what people do in practice. And yeah, I think the inverse equilibrium problem paper really sort of nailed the theory of the idea.
But do you think that the sort of gains in sample efficiency that you have with the methods you've been describing here can be applied in that same setting? Presumably so.
I think so. I think they could help a lot there. Because if you think about sort of the problem, basically learning a policy that controls all of the agents, you could apply everything I described very directly, right? Mm-hmm. I think instead of you're trying to learn something that's a little bit more factorized, I think there's interesting questions there about like how exactly you should do resets. I need to think about what I think is actually reasonable there. Yeah, because I can imagine that you sort of, I don't know if you want to like you might, for example, want to basically reset to states where you actually use some of the data from the current estimates of the other policies rather than just the demonstrations. And I don't know off the top of my head if that's going to make things worse or better, because it seems like it should make things better in terms of just robustness to compounding errors, but I think it also introduced instabilities into the training process. And I haven't thought well enough to kind of know. It's a thing I've been trying to think about, but I unfortunately don't have like a kind of a clean and good answer.
Very good. Are there any other questions from anybody? I'm definitely still interested to hear a little bit more about this. Was it the ADREL algorithm?
Yeah, of course. So that was just I think an interesting idea. It's an old idea. So the older version of this is an algorithm called MMP, or max margin planning. Nathan Ratliff did it back in the day. Also, I'm quite sorry if you can hear the plane flying overhead, but for certain problems, for when you're doing this sort of inverse RL thing, right? Like we're learning both our reward function and a policy, right? And for self-driving, you often care more about the learned reward function. So you can then combine it with like, a test time planner and for safety constraints and other things. But for certain problems, maybe you actually only care about the policy. And then the question is, well, why do I actually need to learn a reward function if I'm not going to use it for anything? Why do I actually need to learn a discriminator? So we go through the full derivation in the paper, but basically there is effectively like a closed form expression for how you should set the rewards, but that you can basically think of the discriminator as basically being like this complicated thing in function space, and the reason you can represent this complicated function is that you're only evaluating it when you're doing policy improvement based on samples in your replay buffer. So you only need to basically just change the labels of the rewards in your replay buffer. The actual algorithm is very simple. Basically, everything that's from the expert gets value +1 in your replay buffer, and everything that is from the learner gets value -1. And then over every round, you kind of decay that -1 with a sort of harmonic series. So on the second round, it's -1/2, -1/3. And this comes with pretty strong guarantees. And there was sort of earlier work, actually my old grad student worked on this. There was an algorithm called Squil, SQIL, that basically just set all the rewards in for the learner to be +1. Sorry, all the words for the expert to be +1, and all the words from the learner to be -1. And that algorithm is very simple to implement. It has no real guarantees, but it also fails really catastrophically sometimes, which we kind of point out in this paper, which is that as soon as the learner starts to actually act like the expert, if you start to still keep giving them -1 rewards, right, they're going to think that what they're doing is incorrect. And then they're going to effectively start doing random things. So effectively, this sort of like annealing the rewards towards 0 was actually very important for both in theory and practice. So yeah, the reason I like that is because it's a very simple algorithm to implement. It works very well, at least in my experience. I actually learned like a year ago that I think the results in our paper are actually worse than they should be. I was working with an undergrad who decided to re-implement it, and he got way better results than I did. So I think it's a sort of thing where, yeah, it's an interesting idea that I hope people use. If it's a problem where you don't actually care about learning the reward function.
Nice, thank you so much. Are there any other last-minute questions? Looks like no, but thank you enormously for that. That was a really, really interesting talk. I think we have a lot to think about there. And yeah, anytime if you want to come back and give another talk at Shocklab, you will be extremely welcome. Wonderful.
Thank you so much. I appreciate it, and thank you for reaching out. And yeah, it was. Thank you for all the questions. I really appreciate it.
Pleasure. Great.
Thank you
Thanks,
so
everyone.
much. Thank you.
See you all soon.
Cool.
Cheers.
Thanks.
Bye for now.
Everybody.
Bye-bye.
Thanks. Bye.
Cheers. Thank you. Bye.
Bye.